Hello students, today we'll talk about force and or flexibility method. Remember from last lecture, we classified the structures into stable structures and unstable structures. The stable structures classified into two parts, indeterminate structures and determinate structures. And remember from last lecture, we can solve the determinate structures by using equilibrium equations. Indeterminate structures, we have several methods can be used to solve indeterminate structures. One of these methods is the force and is also called flexibility method. Force method or flexibility method. This method is the relation by using the relation between action and displacement. The relation that exists between action and displacement plays an important role in structural analysis, and it is used extensively in both of the flexibility and stiffness methods. So this relation between action and displacement is for two different methods, force method or flexibility method, and we will talk next lecture about the stiffness method. So this relation in both methods, but each method has different equation. A convenient way to express the relation between the actions of the structure and the displacement of the structure is by means of action and displacement equations. A simple illustration of such equation is obtained by considering the linear elastic spring. So we'll use the spring as a model to represent force method and stiffness method. The action P, which is applied load P, will compress the spring, thereby producing a displacement delta at the end of the spring. The relationship between the applied force P and the producing delta can be expressed by a displacement equations. This equation is delta equals flexibility times applied force P. In this equation, force or the flexibility, F is the flexibility of the spring and is defined as the displacement produced by a unit value of the action P. So the unit for the flexibility is displacement per unit force, like meter per Newton, inches per pounds. So it is unit displacement per unit force. The relation between the action P and displacement delta for the same spring can also be expressed by an action equation which gives P in terms of delta. P equals K delta. This relation for next method, which represent relation between force, stiffness, and displacement. In the previous equation, the stiffness of the spring is defined as the action required to produce a unit displacement. It can be seen from the previous two equations that the flexibility and stiffness of the spring are inverse to one another. The flexibility of the spring has units of length divided by force, while the stiffness has unit of force divided by length. The unit of flexibility is meter per Newton. In stiffness method, it is Newton per meter. Or you can use any other units for force or length. The same general relationship that apply to the spring will also hold for any linear elastic structure. that is subjected to a single action. An example is given in the figure below, which shows a simply supported beam acted upon by a concentrated force P at the midpoint. So as in this graph, we have simply supported beam, length L, and the action force in the middle of this beam. The producing deformation is delta. The displacement delta shown in the figure above is the vertical downward deflection of the beam at the point where P acts upon the beam. The action and displacement equations are valid for the beam in the previous figure. It is provided the flexibility F and the stiffness K. They are determined appropriately. In this case, the flexibility F is the displacement produced by a unit value of load. So for this figure, the flexibility for this structure F equals L cubed over 48 EI, in which L is the length of the beam and EI is the flexural rigidity. The stiffness K equal to the inverse of flexibility, which is the action required to produce a unit value of displacement. So K is reciprocal of F, 48 EI over L cubed. This simple relationship is valid only when the structure is subjected to a single load.